Today we're going to start looking at chapter 3, and this is a chapter on determinants. Now, determinants is a very important topic in linear algebra, as we are going to see. First off, we have briefly seen determinants before. In chapter 2, theorem 4, we saw how to calculate the inverse of a 2 by 2 matrix. We basically saw if you have an 2 by 2 matrix, A, B, C, D, then you can get the inverse by getting this number, 1 over AD minus BC, and multiplying it by those numbers. So it's very easy to get the inverse of a 2 by 2 matrix. But this number on the bottom, this AD minus BC, note what this says. Well, this is 1 divided by that number. So if that number is 0, that means there's no solution. When AD minus BC is equal to 0, there is no inverse. If it is not equal to 0, then you have a solution to this. This number, AD minus BC on a 2 by 2 matrix, tells you whether or not the matrix has an inverse. That is a special number called the determinant, as denoted by det of A. So when you have a 2 by 2 matrix, right away, there is a number that tells you whether or not there's an inverse, and it's called the determinant. What we're going to see is that for larger matrices, this determinant, and we're going to see how to calculate it for larger matrices, also tells you whether or not there is an inverse. If it's equal to 0, there is no inverse. If it's not equal to 0, there is going to be an inverse. Now, calculating the inverse isn't always as nice and easy as this, but it tells you whether or not there is an inverse. This determinant takes any square matrix and associates with it a number. That number has some really nice properties. One of them tells you whether or not it's inverse, but we're going to see that there's other properties that you can get from the determinant, things that the determinant tells you about your matrix. And in this course, we're only going to touch on some of them. The determinant for a square matrix is really one of the most important concepts when you're studying matrices. So first, an example. We saw the 2 by 2 matrix. We can get the determinant by taking the product of the two numbers along that diagonal and subtracting the product of the two numbers along that diagonal. So it's 2 times minus 4 minus negative 1 times 3, which in this case gives us minus 8 minus minus 3, which is minus 5. That's quickly how we calculate the determinant. So one of the things we'll see with the determinant is, for example, this problem. If we have this matrix with a variable in the matrix, what values of that variable allow the matrix to be inverted? In other words, the matrix is invertible for which values of S, and it's not invertible for what values of S. We can solve that, we can figure that out by using the determinant. So we take that matrix and calculate the determinant of that matrix. So the determinant of 8 minus S for negative 2, 2 minus S. Well, how do you get that? Well, it's the product of the two numbers along the diagonal. 8 minus S times 2 minus S minus the product of the numbers along the other diagonal. Negative 2 times 4. So what do we get for that? Well, 8 minus S times 2 minus S gives us 16 minus 2S minus 8S, so it's minus 10S plus S squared minus negative 2 times 4 is negative 8. So that determinant is equal to, that'd be 16 plus 8. To rewrite this, I get S squared minus 10S plus 24. And now we know how to factor this. You should know this from high school and from first year calculus. You can factor this as s minus 6 times s minus 4. So now we know what the determinant is. The question is, for what values of s is there an inverse? Well, there's an inverse when the determinant is not equal to 0. So when is the determinant equal to 0? So the matrix has no determinant, or sorry, the matrix has no inverse if s minus 6 times s minus 4 equals 0. So when does that happen? Or when s equals 6 or s equals 4. In either of those cases, there's no the determinant is 0. So in either of those cases, there's no inverse. Then we can say that the matrix has an inverse in all other cases. If s is not equal to 6 and s is not equal to 4. So the determinant is giving you a quick way of telling whether or not that matrix has an inverse. It doesn't tell you what the inverse is, but it does tell you whether or not there is an inverse. Okay, so now we're going to start looking at how to calculate a determinant for a larger matrix. But first we're going to need this definition and this concept. We're going to look at something called cofactor expansion. So first off, what is a cofactor? Well, first definition. If you have a square matrix, an n by n matrix, what we're going to do is we're going to eliminate a row and a column. We're going to take the ith row and the jth column and get rid of them. What do we have left? Well, now we have an n minus 1 by an n minus 1 matrix. It's one row smaller and one column smaller. We give that the term Aij when you take the ith row and the jth column and eliminate them. You get a smaller matrix. Now using that, we have something called a cofactor. So if you have an n by n matrix, the ij cofactor of that matrix is denoted by capital C ij, and it's calculated in this way. You take the ith row and the jth column, take them out, and take the determinant of what's left. So you have a smaller matrix, you get the determinant of the smaller matrix. And you multiply it by -1 raised to the I plus j, where it's the ith column and the jth column that you took out. So that's either going to be a +1 or a -1 times the determinant of that smaller matrix. That's called the cofactor. So here's an example. We have a 3 by 3 matrix here, A. We're looking for the cofactor, the 2, 3 cofactor. So to get the 2, 3 cofactor, we have to find A2, 3. So you remove the second row and the third column. What do you get? Remove the second row and the third column. You end up with this matrix, a 2 by 2 matrix. Now, a 2 by 2 matrix, we know how to get the determinant. So we want to get the cofactor, the 2, 3 cofactor. It's -1 raised to the 2 plus 3 times the determinant of A2, 3. -1 to the 2 plus 3 is -1 to the 5. The determinant of A2, 3 is the determinant of that. We know how to get that determinant. It's 2 times 2 minus 1 times 2. There's the determinant. So it's -1 to the 5 is -1 times, that's 4 minus 2. So it's -1 times 2. The 2, 3 cofactor is equal to -2. That's how you get the cofactor. And you see what we're doing here is we start with a square matrix of a certain size, and then we're looking at the determinant of a smaller matrix. But now, remember the question is, how do we get the determinant? So how would we get that determinant of the 3 by 3 matrix? Well, here's the answer, and it's using cofactors, using something called cofactor expansion. So what we do is we take an entire row, and we look at all the cofactors of that row, and then we do some calculations with them. And what we're going to get is the determinant of the bigger matrix. So here's the definition. For an n by n matrix A, the determinant is calculated by doing the cofactor expansion along the first row. So the determinant of A is equal to the 1, 1 term in your matrix A times the cofactor 1, 1 plus the second number in the row, the A12 number, times the cofactor C12, and so on all the way down your entire row until you get to the final entry. So it's the number, the last number in that row, times the cofactor when you take out that first row and the last column. That gives you the determinant of your bigger matrix. So let's take a look at using a cofactor expansion to get a determinant of a 3 by 3 matrix. So if we're given this matrix A, we want to calculate the determinant of that matrix. So remember the definition. The determinant of A is equal to, you look along the first row, and it's the cofactor expansion along that row. So from the definition, it's the first term, A11, times C11, the cofactor, the 1, 1 cofactor, plus A12 times C12. Then to the third number, A13 times C13. Okay, so you just go along the first row and you do this, the number times the cofactor. So now we have 6 things in here. What are they all? Well, first off, A11. Well, A11 is just the 1, 1 number in the matrix. So it's equal to 2. That number right there. A12 is equal to 1, and A13 is equal to 2. So it's the first number in the row, the second number in the row, the third number in the row, and you would continue on if you had bigger matrix. So that's the easy one. Now, what are the C11s? So C11, the first one we have. Remember, this is the 1, 1 cofactor. So it's equal to -1 to the 1 plus 1 times the determinant of the matrix you get when you eliminate the first row and the first column. So you're left with 2, 1, 2, 3. So what's that equal to? -1 to the 1 plus 1 is -1 to the 2 times, what's that determinant? Well, it's the determinant of the diagonal, 2 times 3, minus the numbers along the other diagonal, 1, 2. Well, -1 to the 2 is just equal to 1 times, what's this equation? That's 6 minus 2. So that's going to be 1 times 4. That's equal to 4. There is the 1, 1 cofactor for this matrix. Now continue on to the next one. What's the 1, 2 cofactor? C12 is equal to -1 to the 1 plus 2 times the determinant of what you get when you eliminate the first row and the second column. So go back to A, take away the first row and the second column, we get 4, 1, 2, 3. So simplify this, you get that's -1 raised to the 3 times. We can get the determinant of a 2 by 2 matrix. In this case, it's 4 times 3 minus 1 times 2. Simplify. Negative 1 raised to the 3 is negative 1. Our other equation here gives us 12 minus 2. Simplify it, you get negative 10. The 1, 2 cofactor of the matrix is negative 10. Now our final one is C13. That's equal to negative 1 to the 1 plus 3 times the determinant of what you get when you eliminate the first row in the third column. So what are we left with? 4, 2, 2, 2. So we have negative 1 raised to the 4 times 4 times 2 minus 2 times 2. So we have negative 1 to the 4 is equal to 1 times 8 minus 4. So that's equal to 4. So there's all the elements. Now we just have to put them together using our determinant equation. So that's our A. And remember the determinant of A was equal to A11, C11, plus A12, C12, plus A13, C13. That's equal to A12 was 2. We calculated that C11 was equal to 4, plus that's a 1 times negative 10, plus 2 times 4. So that's equal to 2 times 4 is 8, minus 10, plus 8. That gives us, add those together, you get 6. There is our determinant. The determinant is 6. Right away we know that because that's not 0, there's going to be an inverse for A. Now this determinant is going to tell us other things, but we know right away that A has an inverse because the determinant is non-zero. So this leads us to Theorem 1. Theorem 1 is basically the definition of the cofactor expansion that we just saw. But what we did, remember in our definition, we said the determinant was equal to the cofactor along the first row. The reality is you can do that cofactor expansion along any row or any column. You are going to come out with the same exact thing every time, no matter which row or which column you pick. And that is the determinant. So Theorem 1 says the determinant of any square matrix can be computed by cofactor expansion across any row or down any column. The expansion across the ith row is given by this equation. So this is saying just take the first number in that row times the associated cofactor. Keep going all the way down to the row until you get the number in the last number of the row times the associated cofactor. Or you can do it down a column and it gives you that equation, which is the first number in the column times the cofactor all the way down plus the last number in the column times the associated cofactor. You can do that for whichever one you want, and you're going to come out with the same number every time. That number is called the determinant. So, as an example, take that matrix. Let's calculate the determinant using the cofactor expansion along the second column. Now, this matrix should look familiar. It's the one we did a few minutes ago, where we saw that the determinant was equal to 6. Well, now we're going to calculate it using a different column. We're going to do that column. We're going to calculate the determinant using cofactor expansion along that column. So the big things we need here are the cofactors for each number along there. So we're going on the second column. So we need the cofactor C12, which is equal to, well, that's equal to negative 1 to the 1 plus 2 times the determinant of what you get when you eliminate the first row in the second column. You have 4, 1, 2, 3. So that's equal to negative 1 to the 3 times that determinant, which is 4 times 3 minus 1 times 2. That's equal to negative 1 times 12 minus 2, that's 10. So we have negative 10. Now we move down to the second one. C22 is equal to negative 1 raised to the 2 plus 2 times the determinant of what we get when we eliminate the second row in the second column. So 2, 2, 2, 3. So it's negative 1 to the 4 times 2 times 3 minus 2 times 2. That's equal to negative 1 to the 4 is equal to 1 times, that's 6 minus 4, that's 2, so that's equal to 2. And the final one is C32, so the third number in that column. So that cofactor is negative 1 to the 3 plus 2 times the determinant of what you get when you eliminate the third row in the second column. So it's 2, 2, 4, 1. So that's negative 1 raised to the 5 times 2 minus 1 minus 2 times 4. So negative 1 to the 5 is negative 1 times, that's 2 minus 8, negative 6. Negative 1 times negative 6 is 6. Now we have the cofactor expansions, or the cofactors for all the numbers along that row. The determinant of A is the cofactor expansion. So that was A12 times C12 plus A22 times C22 plus A32 times C32. That's just using the definition of a determinant. What do we have? A12 is equal to 1. C12 is negative 10 plus 2 times 2 plus 2 times 6. This gives us negative 10 plus 4 plus 12. That's 16 minus 10. That gives us 6. Same exact answer we had before. So you see, no matter which row or column you take, you are going to get the same exact result, and that is the determinant of the matrix. And notice what we did here. We're looking for the determinant of a 3 by 3 matrix. What do we do? Through the cofactor expansion, we've reduced it down to getting determinants of 2 by 2 matrices, which we know how to do. Well, now we know how to get a determinant of a 3 by 3 matrix. What if you have to get the determinant of a 4 by 4 matrix? You do a cofactor expansion. What does that do? Then it gives you an equation for getting the determinant of a 4 by 4 matrix using the determinants of 3 by 3 matrices. And we know how to do that. So you see, what it does is it tells you how to get the determinant of a given matrix using the determinants of smaller matrices. So a couple more definitions. If we have a square matrix, we say the main diagonal is the entries A11, A22, all the way down to ANN. So if you have a square matrix, the main diagonal are all the numbers going down there. We say a matrix is diagonal if everything off the main diagonal is 0. You may have zeros in your main diagonal, but if everything that's not on the main diagonal is 0, that's a diagonal matrix. So here's a couple of examples. There's your diagonal. Everything else is 0. The second one, there's your diagonal. Notice it has a 0 in the diagonal, but the key is that everything off the diagonal is equal to 0. That's called a diagonal matrix. Then we also have triangular matrices. So a matrix is upper triangular if all of the entries to the left and below of the main diagonal are 0. So this first matrix is upper triangular because we have the main diagonal. Everything down below it, all of this stuff, is 0. So everything below the main diagonal is 0. Lower triangular matrix is that everything to the right and above the diagonal is 0. So we have our main diagonal. Everything above and to the right is equal to 0. That is an upper or lower triangular matrix. And notice that if you have a diagonal matrix, such as this one, well, everything above is 0, so it's lower triangular. Everything below is 0, so it's upper triangular. A diagonal matrix is both upper triangular and lower triangular. So let's look at an example of this. Now, upper and lower triangular matrices have the very nice property that you can calculate determinants very easily for them. And here's why. Take this matrix and let's calculate the determinant of this. So what's the determinant of this according to our equation? The determinant of A, let's take the first row. So we're going to do the cofactor expansion along the first row. That's equal to A11 times C11 plus A12 times C12 plus A13 times C13 plus A14 times C14. So what's that equal to? Well, A11, that's the first number in the row. That's equal to 1. C11, what's that equal to? Well, that's equal to -1 to the 1 plus 1 times the determinant of what you get when you eliminate the first row in the first column. So it's -2, 0, 0, -2, 3, 0, -2, 500, and 4. Okay, so there is the first term. What about the second term? Well, the second term is A12 times the 1,2 cofactor. What's A12? A12 is 0. So no matter what the cofactor is, that term is 0. Third term is A13 times a cofactor. A13 is equal to 0. And the fourth term is A14 times the cofactor. A14 is equal to 0. So you see, you're left with a single term. Everything else turns to 0. So what's this first one equal to? Well, that's equal to 1 times -1 to the 1 plus 1. Well, that's just equal to 1 times the determinant of this. Well, another determinant. We have to calculate this out. Let's do the cofactor of the first row. Cofactor of the first row of this is equal to the first term, -2, times the determinant, times the cofactor when you eliminate the first row and the first column. So that's equal to -1 to the 1 plus 1 times the determinant of what's left of 3, 0, 500, and 4. What's that equal to? Well, that's equal to 1 times. Well, 1 times 1 is equal to 1. What are we left with here? -2. -1 to the 1 plus 1 is again 1 times the determinant. Oop, another determinant. But now we know how to calculate this. This is a 2 by 2 determinant. So what's this equal to? This is 3 times 4 minus 0 times 500. What's this all equal to? This is equal to 1 times -2 times, well, it's times 1, so we'll ignore that, times 3 times 4. Sorry, -2 in there. So what's this? Take a look at these numbers, 1, -2, 3, 4. That's exactly the diagonal. So you multiply that out, you get -24. But the key point here is when you want to get the determinant of a triangular matrix, whether it's lower triangular or upper triangular, it's actually just equal to the product of everything along the diagonal. Everything else becomes zeros. Everything else disappears. So you can take this and make up your own matrix. Make up any diagonal, any triangular matrix, figure it out, and the long way, and you'll see that the determinant of any triangular matrix is simply equal to the product of the numbers along its diagonal. And this is our next theorem. If we have a triangular matrix, the determinant is the product of the entries on the main diagonal. Another example. We want to find this determinant? Well, we just have to take a quick look at the matrix. It is an upper triangular matrix. So because it's upper triangular, we can get the determinant very easily. So the determinant of A is equal to 7 times 5 times -3 times -5. Multiply these all out. What do you get? You get 7 times 5 is equal to 35. 3 times 5 is equal to 15. So 35 times 15, if you multiply that out, is equal to 525. See how easy it is to get that? If that was not a triangular matrix, you would have to do the cofactor expansion, and you have to do a lot of terms. So there's our introduction to determinants. As I said, determinants is one of the very important concepts in linear algebra. And the immediate thing it tells us is about whether or not a matrix is invertible. We've now seen how to calculate a determinant, and we're going to be studying determinants more in depth.